Hello, welcome to session number 4. In today's sessions, we're going to look a little bit closer at energy band diagrams, specifically one aspect of those energy band diagrams, the band gap. And we'll take a look at that in some detail. And then finally, we're going to look at optical properties. Well, it seems like it's just a couple of topics, but there's a lot to cover. But before we get started, let's listen to the finale of Beethoven's Third Piano Concerto in a marvelous performance by Alice Sarah Ott. She just radiates beauty and competence, and it's just a wonderful, wonderful performance. So enjoy, and we'll see you back in about 6 minutes or so. Okay, so before we get started on the bulk of our material, which our first topic will be band gap dependence on the atomic position of the periodic table, I'd just like to review a couple of issues from session number 3 that popped into my head, and I'd just like to share them with you. First, this guy. Remember Leonhard Euler? Not only one of the most brilliant minds of all time, but also a man of extraordinary humility. And I've always wondered if there's a connection between brilliance and humility. For example, does brilliance drive humility? Or I would suggest perhaps even, does humility drive brilliance? I don't know what the answer is, but just leave the question as an open question for now. Okay, what's in a name? Well, you might remember this is this thing called a ion implanter. Here's the source. Let's just take a look at one particular source, which is phosphine. Phosphorus trihydrogen, or pH3. And this is where the phosphine goes. We strip off the phosphorus from the phosphine as an ion, as a P+. We accelerate it with a series of high voltage electric charges, and the wafers are all the way back here, about 10 feet away. So there's a phosphorus ion which makes its way from the source to the wafers. However, we don't implant ions. We implant atoms. If we were implanting ions, the silicon wafer would become charged. Not only that, the idea of the phosphorus is that it donates an electron to the silicon lattice. Well, if it's already given up its electron back here, there's no electron to donate. So what we have back here at the wafer end, we have a little tungsten wire which supplies electrons, so that what actually smashes in to the silicon lattice is not a phosphorus ion, but rather a phosphate atom. So why do we call it an ion implanter? We should call it an atom implanter. Well, I have my own perverted idea. If you ever talk to a politician and you say, well, I'd like to make an atom implanter, the first thing would probably pop into his pea brain is that it's an atomic bomb, and he doesn't want an atomic bomb in his neighborhood, so he probably wouldn't allow it. But if you say ion, he doesn't understand what an ion is. Nobody understands what an ion is, so it's okay. The same thing concerning MRI, magnetic resonance imaging. That's what the word I was looking for, MRIs. It didn't used to be called MRI. It used to be called NMR, nuclear magnetic resonance. But again, if the doctor told you they're going to put some nuclear stuff in your body, you probably would reject that. So they just changed the name. Instead of nuclear magnetic resonance, which is really what it is, they made it into magnetic resonance imaging, which sounds much less threatening. Okay, so those are just two little review items. Let's get on to the bulk of the material for today. And we're going to start with the energy band diagram. So the point I'm trying to make on this relatively simplistic diagram here is that if the energy is sufficient to kick an electron out of the lattice, it raises the energy goes up, and the electron is able to find itself in a place where it can become mobile. It can actually conduct electricity. So if the electric field, for example, is from right to left in this direction, the electron will move from left to right. So we added a vertical axis, and we call that vertical axis the electron energy. As the energy goes up, the number becomes higher and higher. The energy band diagram is one of the fundamental tools in all of solid-state physics. And here we have Kromer's lemma of proven ignorance, and he won the 2000 Nobel Prize in Physics for his work on drawing energy band diagrams for very special devices. So if you're discussing a semiconductor problem and you're unable to draw the energy band diagram, you don't know anything. If you are able to draw it but don't, your audience won't understand what you're talking about. And I think that's quite a reasonable statement. It just says that the energy band diagram is one of the primary focuses of everything we do in semiconductor devices. Here's an example of a rather messy energy band diagram. And you see it's got lots of different levels and lots of different symbols. And the only symbol that we really, it must be here, oh yeah, there it is, the conduction band edge. Now we're going to see the conduction band edge in almost every energy band diagram that we discuss and draw, and all of these other numbers and levels we'll learn slowly but surely as we learn the different devices. Now let's look at the band gap. What I'm interested in right now is to find out what causes this thing to be either large or small. Clearly, if it's large, it takes a lot of energy to kick an electron from the valence band to the conduction band. If it's small, for example, the conduction band is over here, then it doesn't take nearly as much energy. What determines the band gap? This thing called Eg. Well, let's take a look at part of the periodic table which will be concerned to us. And specifically, we're going to start with column 4. And there are 4 materials. These are single component semiconductors: carbon, diamond, silicon, germanium, and tin. And let's take a look, and I've just circled them here, because that's what we're going to start with. So for the 4th column, they're all semiconductors. The band gap of carbon is 5.5 eV, which is quite large. Band gap of silicon is 1.1 eV, which is moderate. The band gap of germanium, 0.67 eV, and the band gap of tin, which is on the bottom, is less than 0.1 eV. So something about the position of these different materials in the periodic table determines the band gap. As we go down, it seems that the band gap gets smaller. Now, why should that be? Well, as we go down in the periodic table, the atoms get larger. Carbon has 6 electrons and 6 protons in the nucleus, silicon 14, germanium 32, and silicon 50. So as we go down from row number 1 to row number 2, 3, 4, the atoms are getting bigger. As the atoms are getting bigger, the hold on the electrons in the valence bands gets less and less, and the ease to kick an electron from the valence band into the conduction band gets easier and easier. Now, there are other semiconductor materials. For example, we can have one component from column 3 and one component from column 4, and from column 5. column 3, column 5, it kind of averages together to make column 4. So we can have, for example, aluminum phosphide, which should be reasonably similar to silicon. I discussed this quite a bit in the text. We would think at first blush that aluminum phosphide would have a band gap of about 1.1, the same band gap as silicon. It actually works out that the band gap of aluminum phosphide is greater than the band gap of silicon because of something called electronegativity, which we're not going to discuss too much, although I do discuss it quite a bit in the text. Gallium arsenide, 3, 5. The average would be 4. The band gap of silicon is band gap of germanium is 0.67, but the band gap of gallium arsenide is 1.43, which is over twice as much. And the same holds for silicon antimonide. It's much, much greater than the band gap of tin. And finally we have at the ends here zinc selenide, cadmium selenide, zinc telluride, and cadmium telluride. And here the differences are even greater. We would expect, for example, that first blush that zinc selenide should have approximately a band gap of 0.67. It is much, much greater than that because of the differences in electronegativity between zinc and selenium. Well, again, we don't really have to understand that in any kind of detail, but just to note that things are not quite as simple as they would seem. So what we said was, and we go down in the periodic table from a low row to a high row, the atoms get bigger. And that is indicated here by the unit cell dimension. We'll talk about unit cells a little bit later on. Carbon has a small unit cell, and they get bigger and bigger and bigger until tin is much, much bigger than carbon. Here are some of the atoms which can combine to form typical semiconductor molecules. We can have boron nitride in row number 2, aluminum phosphide, gallium arsenide, which is one of the most important, and a few others. In this table, and this comes from chapter 2 in the text, I'm trying to indicate that the column 3 radius of the atomic radius and the column 5 radius, if we average them, we get approximately the radius in column 4. So it's not the radius which determines the band gap. It is this thing called, again, electronegativity. So you can read more about that in the text. And this just summarizes the idea that as we go down in the periodic table, the atomic size increases. There's a larger lattice constant. The atoms in the lattice get further and further apart because they're bigger, and the band gap gets smaller and smaller. So we're asked to calculate the number of silicon atoms in 1 cubic centimeter. And we're given the length of the unit cell, and we'll talk about that a little bit later, 5.43 angstroms. I should talk about it right now. It's the distance between silicon atoms in the lattice in each direction, x, y, and z. Every direction you go, from one silicon atom to the next, from center to center of the atom is 5.43 angstroms. I'll tell you a little bit about what angstroms are. And we're also given the atomic weight of silicon is 28, and Avogadro's number, which I always forget, is 6 times 10 to the 23rd atoms per mole. And then we're asked to use all this information to find the density of silicon in grams per cubic centimeter. And finally, to compare that with germanium, germanium is lower down on the chart here on the periodic table. Silicon is row 3. Germanium 0.4. Germanium is bigger. Its lattice constant is bigger. Its band gap is less. All that is consistent. 5.65 angstroms as compared to 5.43 angstroms. So we would expect less germanium atoms per cubic centimeter than silicon, and we'll see if that indeed is the case. Okay, so here we see the three-dimensional unit cell of silicon. Silicon here, silicon there, silicon there, silicon there. There's 8 silicon in this cube, and the distance between the silicon atoms is 5.43 angstroms. 1 angstrom is 0.1 nanometer. In other words, there are 10 angstroms in 1 nanometer. Thus, the distance in angstroms converted to centimeters is 10 to the minus 8th centimeters, or 10 to the minus 10th meters, because there are 10 squared centimeters per meter. And thus 1 nanometer, well, we know 1 nanometer is 10 to the minus 9th meter, which would be multiplied by 100, 10 to the minus 7th. And just one, actually a rather important number in semiconductor devices, there are 10,000 angstroms in 1 micron. So thus the unit cell, we just take the dimension and we cube it. And we get 1.6 times 10 to the minus 22 cubic centimeters in each cell. And if we flip that, we get cells per cubic centimeter, which is 6.25 times 10 to 21 cells per cubic centimeters. That's the flip of cubic centimeters per cell. Now, since there are 8 silicon atoms per cell, this should be atoms per cell. Cells cancel out. We get atoms per cubic centimeter. There are 5 times 10 to 22 silicon atoms per cubic centimeter. And that's actually a fairly big deal. Now, since there are Avogadro's number atoms per mole, and 1 mole is 28.1 grams, putting all that in, well, this is just the constants, 2 times 10 to 22 atoms per gram. So if we put in atoms per gram time on the denominator, and there are 5 times 10 to 22 atoms per cubic centimeter, we see the atoms cancel out, and we get grams flips on top. Grams per cubic centimeter, 2.3 grams per cubic centimeter, and that indeed is the density of silicon. So germanium is lower on the periodic table, and it scales like the cube. So instead of having, what did we find here, 6.25 10 to 21 cells per cubic centimeter, or I should say, 5 times 10 to 22 silicon atoms per cubic centimeter. Here we get 4 times 10 to 22 atoms per cubic centimeter. Okay, let's go on now to optical properties. And we're going to start with the Einstein relationship. Energy is equal to Planck's constant times the frequency. Now, if Einstein was smart, well, actually he was very smart, but he didn't even have to spend too much energy in deriving this equation. It just pops right out of the units. The units of Planck's constant are what we call action. Momentum multiplied by distance. Momentum is mass times velocity. Distance is L. So mass is kilograms, velocity meters per second, multiplied by meters, we get kilogram meters per second squared. Those units are called action. Now, if we multiply by F, what are the units of F? Cycles per second. So the basic units are 1 over seconds. So that brings another second down here. So we get the units of HF are kilogram meters per second squared. That's just the units of energy. So that's why I say Einstein didn't have to work too hard to develop the equation. He could have gotten it right from the units. Now, in the last, I think it was session number 2, we derived this equation. Velocity is equal to distance divided by time, or frequency is equal to velocity divided by wavelength. And if we substitute this for energy, instead of F, we substitute C divided by lambda, we get the energy is equal to hc divided by lambda. Hc is just two constants, Planck's constant times the velocity of light. And here we have Planck's constant, 6.6 × 10 to the minus 23rd in MKS units. The velocity of light is 3 times 10 to the 5th kilometers per second, or 3 times 10 to the 8th meters per second. So we get 1.98 times 10 to the minus 25th in MKS units. So substituting that into this equation here, we get 1.98 10 to the minus 25th divided by lambda, and the energy here is in joules, and lambda is in meters. Well, this is a really small number. That's not good. We would like to change that to the atomic world, and to do that, just as we did in our first session, we divide by the electron charge, 1.6 times 10 to the minus 19th coulombs per electron. And after we do that, we get 1.24 times 10 to the minus 6 lambda, and now the units of energy are in electron volts, but lambda is still in meters. Finally, since there are 1 million microns per meter, we can translate or transform our lambda from meters into microns just by multiplying by 10 to the 6th, and we get this equation, and this is our working equation. The energy is equal to the energy of a light or any electromagnetic radiation is equal to 1.24, just a simple number, no 10 to the minus blah blah blah. It's just 1.24 divided by lambda, where the energy is in electron volts and the wavelength is in microns. And this is our fundamental working equation. Now this number, it works out for a broad range of lambdas, is very close to the band gaps of many common materials. For example, red light has a wavelength of about 0.6 microns, so its energy would be about 2 eV. Well, where have we seen that before? That is the band gap of silicon carbide and a number of materials which have band gaps very close to that. For blue light, its wavelength is less, so the energy for blue light was 3.1 eV, and that would be considered a wide band gap material. Well, let's look at some examples here. Starting out with indium antimonide. Heavy. Both indium and, antimony. Both indium and antimony are really heavy, and even though they're a combination, we expect a wider band gap. Well, it's certainly wider than tin, but it's very small band gap. So this, it works out, transmits only in the far infrared. Transmits, and we'll talk about that a little bit later on. Gallium arsenide, 1.43 eV, not enough to translate in the visible light. Gallium phosphide, 2.2 eV, it appears reddish, very, very close to the visible range. Silicon carbide is about 2.5, 2.6, 2.7, and silicon carbide is transparent, and we'll see why in just a little bit. Gallium nitride is 3.43 electron volts. That is definitely transparent. Silicon dioxide glass has a band gap, believe it or not, even though we classify it as an insulator. You can think about silicon dioxide glass as being a semiconductor with an extremely big band gap, and that is transparent almost for everything to an extremely large range of wavelengths. Aluminum nitride 6.2 also is transparent for visible light and is transparent really into the deep UV. Al2O3, this is sapphire, aluminum oxide, 9.9, which is actually higher than silicon dioxide, and it is transparent in the extreme UV. And the highest band gap is, as expected, well, not expected, it is composed of two very light atoms. Calcium is very light on the extreme left side. Fluoride is very light on the extreme right side. By light, I mean way up in the periodic table. And that has a band gap of 10 eV. Notice that aluminum is light, oxygen is light. Most oxides have very wide band gaps. Silicon dioxide, we would expect to have a band gap less than sapphire because aluminum is lighter than silicon. So all that makes sense. Okay, so this is from chapter 2. You can read about it. Why do we want materials which have very wide band gaps that transmit deep into the deep UV? And that's because for optical lithography, we use extremely small wavelengths. Deep UV. And we like them to be transmitting. So in order to do that, we need extremely large band gaps. Now here's the secret. Okay. If the band gap, notice this is the band gap from the conduction band to the valence band. If the band gap is less than the energy of the incident light, the energy of the incident light will be able to kick an electron up from the valence band into the conduction band, and the material will be transparent. Examples for indium antimonide, gallium arsenide, silicon. All those materials have band gaps which are less than the incident light for visible light. If the visible light has energy which is less than the band gap, for example, wide band gap materials, glass, gallium nitride, sapphire, there's not enough energy to kick an electron from the valence band up to the conduction band, and the material appears transparent. The light goes right through because it's not absorbed. So that's the secret. Okay. Basically it for chapter 2, and next week we start on chapter 3, Fermi-Dirac statistics. And I'd like to leave you with a little video clip which talks about probability and the antithesis of probability, which is certainty. This is a quote which I have very fond of. I generally flash it on the screen in almost all the courses that I have taught in the past. It's by a quote from Samuel Johnson. Patriotism is the last refuge of the scoundrel. And in the 20th century, Isaac Asimov, famous scientist, sort of had a paraphrase of that. Violence is the last refuge of the incompetent. And I ask students to think about that and come up with your own versions. These are two of mine, which you may feel are silly or not. Certainty is the last refuge of the ignorant, which I think is going to be relevant for our future discussions. And the one that I like the most, mathematics, is the last refuge of the incompetent physics professor. Okay, so we're going to play a clip by Jacob Bronowski, The Ascent of Man. I think you'll find it quite interesting. It describes the evil of certainty. And I played this for a number of my classes, and one class in particular, my favorite class, which was our local state prison, and one of the students there raised his hand after looking at this clip and said, okay, I think this fellow, Bronowski, makes a very good case that certainty is a terrible, terrible evil in the world. But I have a question. What's the difference between certainty and faith? It's interesting, no? And I didn't have an answer. And I went home and I struggled with it. And I came back and next session, we had a little bit of discussion. What is the difference between certainty and faith, specifically religious faith? So you might want to think about that and perhaps come up with your own ideas. Anyway, let's now look at a powerful video, Jacob Bronowski talking about the evils of certainty. And we'll see you next time.
It's said that science will dehumanize people and turn them into numbers. That's false, tragically false. Look for yourself. This is the concentration camp and crematorium at Auschwitz. This is where people were turned into numbers. Into this pond were flushed the ashes of some 4 million people. And that was not done by gas. It was done by arrogance. It was done by dogma. It was done by ignorance. When people believe that they have absolute knowledge with no test in reality, this is how they behave. This is what men do when they aspire to the knowledge of gods. Science is a very human form of knowledge. We are always at the brink of the known. We always feel forward for what is to be hoped. Every judgment in science stands on the edge of error and is personal. Science is a tribute to what we can know, although we are fallible. In the end, the words were said by Oliver Cromwell. I beseech you in the bowels of Christ, think it possible you may be mistaken. I owe it as a scientist to my friend Leo Szilard. I owe it as a human being to the many members of my family who died here, to stand here as a survivor and a witness. We have to cure ourselves of the itch for absolute knowledge and power. We have to close the distance between the push-button order and the human act. We have to touch people.